Newton's laws of motion. The first law of motion states that an object at rest stays at rest and an object in motion stays in motion with the same velocity and in the same direction unless acted upon by an unbalanced external force. With this law we can say that the object will travel a straight path if it is initially moving unless acted upon by an external unbalanced force. Newton's second law of motion states that the acceleration of an object is directly proportional to the force applied to it and inversely proportional to its mass. The original statement of this law is based on the concept of momentum. It states that the rate of change of momentum of an object is directly proportional to the force applied, and this change takes place in the direction in which the force is applied. This is a relationship between mass of the object, the amount of force that will make the object move, and the rate of change in its movement or the acceleration. This means that an object will accelerate, change its velocity, or change its direction of motion if it overcomes equilibrium conditions, meaning there is a net force. Here are the equilibrium conditions. Here are the non-equilibrium conditions. Take note that the positive or negative sign may indicate the direction of the net force present, or acting along their respective axes. The mathematical form of Newton's second law, relating the force, mass of the object, and acceleration is given by where F net is the net force, m is the mass, and a is the acceleration. We have for the x, y, z axis unit of force. The unit of force must be kilogram times meter per second squared, which is called as Newton. So 1 Newton is the amount of force needed to accelerate 1 kilogram of mass by 1 meter per second squared. This is done to honor Sir Isaac Newton, who lived from 1642 to 1727, a great physicist. Two other units of force which we encounter sometimes are the dyne and the pound. We go to Newton's third law of motion. This states that for every action, there is an equal and opposite reaction. In simpler terms, this law states that when one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object. The forces are always of the same type and occur simultaneously. These forces are referred to as action and reaction forces. Mathematically, if object A exerts a force F on object B, then object B exerts a force negative F on object A. The magnitudes of the forces are equal, but they act in opposite directions. To sum up, determining the normal force. We consider the object lying on a flat surface laid perfectly horizontal. We know that the object has mass and it is affected by gravity. Therefore the object has weight. This is equivalent to the force due to gravity. We see that it is directed towards the center of the earth. This force is also directed towards the surface. The surface has to endure this force and must exert a counterforce equal in magnitude, but opposite in direction just to support the object. This is the force acting perpendicular to the horizontal surface, and it is equal to the normal force. Consider the object placed at an inclined plane. The inclined plane makes an angle theta with the perfectly flat horizontal surface. The object has mass, hence affected by gravity, therefore there is a force due to gravity equivalent to the weight. This force is still directed towards the center of the earth. The box is still sitting on the inclined, hence the inclined plane is exerting an amount of force to support the box. This is the normal force in this case. This is equal to the component force acting on an object when sitting on an inclined plane is divided into two parts. We have the normal force and the force acting parallel to the inclined plane. Consider the box sliding downward on the inclined plane. We analyze it using Newton's law of motion. With the law of inertia, we have, following this condition, we test if there is a net force by analyzing the force interacting along the inclined plane. We see that friction should be along the inclined plane. In this case it is 0 Newton. The force along the y-axis is given by. We can now calculate for the acceleration along the inclined plane using where the force parallel to the inclined plane is given by. We have, and because the surface is frictionless, we have, the equation becomes, using Newton's second law we have, divide both sides by m. The acceleration along the inclined plane is given by. Consider the box sliding downward on the inclined plane under the effect of friction. We know that the forces acting along the inclined is given by. We need an equivalent expression for the normal force N. We can get this from substituting it to the equation we have. We equate it to Newton's second law. Divide both sides by m. The acceleration of an object in an inclined plane in the presence of friction is given by. Consider the box sliding downward on the frictionless inclined plane supported by a rope tied on a pulley which is not allowed to rotate. We notice that there is a tension force present along the rope. The sum of all the forces along the inclined plane is given by. We get the sum of all the forces along the y-axis is given by. We can find the tension present in the rope is given by. In this frictionless inclined plane, we hung another mass using the other end of the same rope as shown in the diagram, and not allowing the pulley to rotate. We see that there is a tension, T sub 2, developed along the rope due to the weight of the second object. The sum of all the forces along the y-axis is given by. We also see that there is no acceleration along the x-axis for mass 2. Since they use the same rope, the tensions are interacting with one another. The resulting interaction would result to the movement of the two objects in the same direction. If we allow the pulley to rotate, it will rotate to the direction of the net force. We have to assume turning in a clockwise or counterclockwise direction. This helps in assigning if the sign is positive or negative for each force or tension acting on the system. We assume that the movement will in favor the heavier mass. The equation of motion for mass 1 are given by. The equation for mass 2 are given by. The sum of the tension along the rope is given by. Assuming that mass 1 is greater than mass 2 and the movement will be downward the inclined plane, we have relating the acceleration to the total mass in the system, then knowing that it is related to the net force and is equivalent to the present tension. We have simplifying gives the acceleration of the objects m1 and m2. Assuming that mass 2 is greater than mass 1 and the movement will be downward the path of mass 2, we have relating the acceleration to the total mass in the system, then knowing that it is related to the net force and is equivalent to the present tension. We have simplifying gives the acceleration of the objects m1 and m2. Consider the presence of friction along the inclined plane. The sum of all the tensions in the rope is given by. The sum of all the forces along the inclined plane for mass 1 is given by. And the rest of the equations are still the same. We see that the acceleration of the objects is equal to